if you have Al F3, if you're trying to decide what type of bond there's going to be, there's a few things you can look at. You look at whether the elements involved are metals versus nonmetals. You look at maybe electronegativity differences. And you look at the noble gas configuration. Those three should all work hand in hand. So you can really use any one of them, but I would definitely recommend using 2 or 3 of them to be more confident that you've come up with the right answer. So in this case, looking at 1, we've got a metal and a nonmetal. Right? So again, the cutoff is this staircase here, where the nonmetals are on the upper right of that, the metals are on the lower left. There are some elements that are kind of like right on the staircase that are called metalloids. And they have some properties of metals and some properties of nonmetals. So I mean, that's where you recognize that you can't just use this as your only standard to determine whether elements are going to be bonding covalently or ionically. Because the metalloids can be involved sometimes in an ionic bond, sometimes in a covalent bond. So we have to look at these other 2 factors as well. But generally, if I have a metal and a nonmetal, I should usually predict they should be ionic. If the electronegativity difference is very large, then I also would normally predict it would be ionic. But that's not always the case either. So if you look at the electronegativity table that is on page 194, the electronegativity for aluminum is 1.5, and for fluorine it's 4.0. It's a pretty big difference. Most textbooks kind of create a bit of an arbitrary cutoff of 2.0. So if the difference between the electronegativities is 2.0, you'll often hear textbooks say if the difference is 2.0 or more, it should be ionic. If it's less than 2.0, it might be covalent. But there are lots of exceptions to that. So again, you don't want to use this rule as your only judgment in determining whether a bond will be covalent or ionic. So here I have the electronegativity differences between the 2 elements involved in the bond. 4.0 minus 1.5, that gives me 2.5. So since the electronegativity difference is greater than 2, so this metal and nonmetal joining together suggests it's ionic. Electronegativity difference of greater than 2.0 suggests it's ionic. And looking at number 3, which is probably the biggest factor, maybe I should have numbered it number 1, but the noble gas configuration is probably the biggest driving factor. So if these elements can make a noble gas configuration by not sharing, then almost every time they will not be sharing. There are very few exceptions to that. If the only way they can make a noble gas configuration for each element is by sharing, then they will almost always be sharing. So that's what we have to analyze. So if we look at the aluminum, as a neutral atom, it would have 3 electrons. If we look at the fluorine as a neutral atom, it would have 7. So they're both kind of within reach of a noble gas configuration by either losing or gaining electrons. Right? So I'm not going to share, because if I shared, the aluminum would have to pick up 1, 2, 3, 4, 5 more electrons to make the same number as a noble gas. So the fluorine would have to share 5 of its 7 with the aluminum, and the aluminum would have to share some with it. That's not very reasonable, because the aluminum is not, first of all, the aluminum's electronegativity is low, which means at 1.5 it's not really able to bring in extra electrons. So even trying to get it to attract 1 or 2 extra electrons is not easy. It's low attraction for shared electrons. But trying to put 5 electrons on is way too many. And when it's only 3 away from neon, all it has to do is lose 3 of its 13 to get down to 10. That's much more reasonable. So that's why we normally predict for a metal it's much more likely to exist with a charge. To get a noble gas configuration, same number of electrons as a noble gas, and the fluorine only needs to pick up 1 to get a noble gas configuration. So in the third aspect of this analysis, we can say if a noble gas configuration can only be reached without sharing, then it should be ionic. And that's what we have here. So we're going to create these charges in order to make a noble gas configuration. And then the formula that we have is going to involve a ratio of those two charges so that the overall charge is balanced out. We need 3 negatively charged fluorides to balance 1 3 plus charge on an aluminum. So that was question 5.109.